we don't have one equation with two time variables in it. We have two equations with two different time variables in them. So this is a different kind of thing which has not been studied very much. And so when you think about how to solve this equation, first of all you realize that really, among the space-like configurations, there are two kinds of space-like configurations. I call them with respect to, if you take an initial surface, with respect to that initial surface, there are space-like configurations that are quote-unquote far away from each other in the sense that their backward cones, their paths do not intersect. And then there are space-like configurations where their path does intersect. If you look at the first kind, for those that are far away, there is really nothing to do because they don't know about the other particle. They don't know about the existence of this other thing. So you have initial data there, you can solve that initial data and find a solution for the photon and so you know everything about this wave function. There is no interaction in this case. They have not gotten to each other. But for nearby configurations, it's clear that the paths intersect. So if you solve one of them and then go try to solve the other one, now you need to take into account that because now you have some data coming from the past, like cone of, say, the photon. So indeed, this is how we propose to solve these equations, by doing them one at a time. You start, for example, with the photonic wave equations first. You have your initial data. It depends on both the initial position of the electron and the initial position of the photon. Very good. Take the initial position of the electron to be a parameter. You have equations, solve the photonic wave equations for the initial data given by the initial position of the photon, and think of the SE there as a parameter. You solve the wave equation for the photonic wave equation. Remember, there are two equations to solve. You solve the first equation, you get a solution at all times. This is just, and now you're just solving a linear wave equation. You're going to get a solution at all times Tp, Sp, and they still depend on this parameter, Sp. Now, turn this around. Take this guy that you just got as the initial data for the other one, for the other equations. Now think of Tp, Sp as parameters and solve the electrons equation. It's again another wave equation. This time is massive, but we can solve it. So the free evolution represents really no problem to solve this thing by this iterating way. And what you realize is happening when you solve the second equation is that the coordinates of the photon appear as you are fixing that, and now you are solving the problem for the electron. So this is called the projected configuration of space-time, right? Where you project down on a copy of a space-time, but the location of the photon is now fixed, and the electron is moving around, right? So this is so working in this space, you realize that there is the boundary between far-away configurations and nearby configurations. Remember, it made a difference if they were far away or not. And here, this boundary between these two configurations comes in. This is a different boundary from what I was talking about. To see how that looks like, we can sort of look at this picture here. So this is an example of a far-away configuration, right? And this is an example of a nearby configuration. So the boundary would be configurations that look like this, right? And these configurations, so if you fix this one and start moving this around, right, you will see that you will get this coming out as the boundary, and it's also here as the boundary. It's important to note that this boundary is characteristic. So we are solving a wave equation, right? So we have a wave equation. Normally you think of solving a wave equation with time-like boundaries, but this is characteristic boundary, okay? It doesn't mean that you can't do it. It means that you have to be careful. Because one of the things that hyperbolic equations are famous for is that they're allowed to have singularities on characteristics. And in particular, in this case, the gradient of the solution is allowed to jump across this surface. And in fact, in our solution, it will jump. That's, so this will come up, but this is okay. We understand how this works. This is a diagram of how this configuration, projected configuration of space looks like. We have fixed the location of the photon in the center, and now this is the space configuration, the space of the electron now. And as you can see, there are two regions. Here's that boundary that I was talking about. If the electron is here, we have no problem solving this. This will not see the photon at all. If the electron is here, and we try to solve it, you're going to get information coming off of this part of the boundary, right? And what is this part of the boundary? It turns out that's exactly that C, that coincidence set. So that I was mentioning before. So here's now the full picture. It turns out that what we are actually solving is a Gauss problem. So in wave equation or hyperbolic equation parlance, initial value problems where the initial data is given on a space-like hypersurface, these are called the Cauchy problem. If the initial data is given on a characteristic surface, this is called the Gauss problem. Right? So what we are solving is a Gauss problem. We have data coming from this part here, because we have solved the photon equation, and now we're going to solve for the electron. It will be solved in this rectangle here. Right? The solution will be continuous across here, but you will see the gradient of the solution is allowed to jump across here. And that, so the solution, therefore, generally speaking, you do not expect better than Lipschitz regularity for the solution overall. The solution will be continuous, but its gradient is allowed to jump, but a finite jump. So that's, all right, so here's the theorem with Matthias Lienert and Michael Kiesling. Let S be this space-like configurations. Well, the half of it corresponding to the photon always being to the left of the electron. This is in one dimension you can do that. But of course, in higher dimensions, that doesn't make sense. But in one dimension, you can only restrict to half of the space in this way. Let's take any constant vector field. This will work with anything, right? You have your equations, you have your initial data, and that's the boundary condition. I have not told you where I got this boundary condition from, but I will say that in a second. That comes from this thinking about the particles not going through each other, gives you that thing. And then you prove that this has a unique global solution, continuously depending on the initial data, Lipschitz continuous everywhere, and smooth away from that B boundary. Okay. Moreover, for typical positions of the particles, the Bohmian trajectories. So after you find the wave function, then you can stick it into the guiding equation and find the trajectories for these two particles. So it is not very difficult to show that these trajectories exist globally, uniquely, and in such a way that the photon does not go through the electron, always stays on the same side.
To what extent did the solution, the unique global solution, depend on the choice of X?
How does it depend on X? So, well, just as you see, just as you see there.
Different X's yield different.
Different X's at this stage. This theorem works for any X.
Yeah.
Right. So that's.
Could there be? Could different X's be equivalent in the sense they yield the same solutions?
Well, the extent of dependence on X is exactly what you see.
Exactly
what you see there, right? But of course, the X that we will actually be using this for will be constructed out of the initial data for the site itself. But in general, you could think of doing it for any X.
But right now, you haven't told us what other role this X is going to play.
Well, okay, yeah, that's right. It's coming up. There's one more thing that this X does. So good question. So, but first about the boundary conditions. Where did I get that formula for the boundary condition? It comes from exactly this idea of the particle current being conserved, right? So you don't want any flux from one side of this configuration space to the other side, meaning you don't want the particles to go through each other. And if you write that and stare at that, you realize that this is actually the same as saying that the relative Bohmian velocity is 0. So, and it's easy to see that wave function satisfies a free evolution in each set of particle coordinates, so they are interacting solely via this boundary condition.
So the notation here says that you're actually using that very x from before to define the Bohmian velocity.
Yes,
The x
yes,
is
yes, exactly. Yeah, yeah. This is how this x plays the second role.
Do different choices of boundary condition correspond to different choices of the self-adjoint extension of a minimal Hamiltonian?
It is possible, yes, yeah.
That often
Yeah.
comes up.
Yeah, yeah, this could be, yeah, indeed, this is not the only boundary condition that works for these equations, because there's this part of a whole family of things.
That would be different dynamics or different?
They will get different dynamics, because it will sort of say that the particles are partially allowed to go through each other or something.
Yeah, yeah.
Right, so that's in a precise mathematical.
Phase shift or something.
Right. So in fact,
Bohmian velocity is the speed of light?
no, it's not. You will see what it is. It's coming up. So that's so then there's this theorem which says that if you start with that general form of the boundary conditions, if you start with that and demand Lorentz invariance, which you should, you only get the thing which I wrote down. That's the only possibility. So there isn't really that much freedom. You see, that was a quadratic condition on the wave function. This is a linear condition on the wave function. So that's important to see that this comes up. Okay, so now we get to see some movies. Hopefully this works.
So you said before
Yeah.
that the x, which you used to define the Gauss equation,
Mhm.
is determined by the wave function.
Yes.
And I guess you showed how it actually is determined by the wave function. because you-
I didn't show it. I didn't show it.
But you saw x in the wave function, so you can imagine, I suppose, that actually it's determined by the wave function.
It is determined by the wave function in a very specific way, which I'll explain to you afterward. We can construct it just from the initial data for that. So it doesn't. So in a sense, you don't have to solve the equation first in order to see what is x. Does that make sense?
Yeah.
Once you have the
that's
initial
question.
data,
Is x an
right,
additional parameter in the theory,
right.
or is it, as you said,
Right.
determined by the wave?
Yeah, it's determined by the initial data. So okay, so what we are going to see is going to be a movie of the density. So what I'm going to be plotting is the wave function, modulus of the wave function square, which normally is identified with the probability of finding that configuration, right? So because the space is one-dimensional, the configuration space, the configuration space as it evolves in time will just be two-dimensional. So you will see this thing. And first, I'm going to show you the non-interacting case. So if you have just two particles that are not interacting, one of them is photon and the other one is an electron, the photon is going to go along characteristics. That's the wave equation of the photon. And the electron is going to be spread also inside because it's a massive wave equation. So the horizontal axis is the photon position, the vertical axis is the electron position, and what we are looking at is the density plot of the modulus psi squared as it evolves in a common time. So we have set the two times equal to each other to be able to get a movie out of this. This normally would be a four-dimensional space. So this is some way of trying to view that four-dimensional space. And as you can see, you start here in the center, which means that here the electron is at position 1 and the photon is at position 0. The wave function has four different components. all four components evolve according to wave equations. So as you can see, they're going to start, they spread out, all four of them, and the situation is completely symmetric. And in particular, this diagonal line is where the photon and electron are at the same position. So this bump is going through, meaning the photon and electron just went through each other. So this is the non-interacting case. Does this make sense? So when they don't interact, there are four components. Three of them move away. One of them just goes right through the boundary, right? And so this means they just went through each other. Okay, so now what happens if I turn on the interaction? So now I'm solving the equations, and I'm taking that boundary condition into account.
An interaction means only the boundary condition.
That's just the interaction. So now you can see the interaction. You have the same four bumps, but one of them moves towards the boundary and gets reflected. And so this means that all of the dynamics is now restricted to half of the space, where the photon is always to the left of the electron in this example. So yes.
Can you change the sign of the boundary condition? Can you get bound states?
Can I get bound states? That's a very good question. Just, I will show you some pictures at the end.
Sort of, yeah.
I think we may already have bound states, but the question is, the way I'm looking at it, those correspond to initial conditions that are not typical. So, but with the specific initial condition, we may even get bound states. But that's something that we are still thinking about. Okay, so that was this is just we can move on. This you already explained that. So what happened? Okay. So now trajectories. We have the wave function. Now we can solve the ODE, the guiding equation, and get the trajectories for these particles. So what we need for this theory is called the hypersurface Bohm-Dirac model. This is a relativistic generalization of the Dobrody-Bohm guiding law, which was done by Shelley and collaborators. So it needs two ingredients. One is a relativistic current that's a tensor product of one-body currents. And we do have one-body currents because we knew a current for the electron already, thanks to Dirac, and we constructed one for the photon. So if we take their tensor product, we have our one-body current. And the other thing you need for this theory is a space-like foliation of the space-time. And we have that also thanks to this vector field that we have constructed. So we are going to use that vector field to give us this foliation of the space-time with respect to which these dynamics are defined. In particular, we'll go into a frame where this vector field is just the 1-0 vector field, and then we could look at the equations for the two particles. These are just two ODEs, and here was your question, Joel. This is the velocity of the one of the particles, and this is the velocity of the other particle. J was this tensor current, right? So J 0, 0 in the denominator, we can think of that as rho, and this one up here is the V. Right? So sorry, this is the current, so the ratio is the V. So that is the other V. Right? And the boundary condition that we have is that when the two particles are at the same location, this difference between these two is 0. So they are the same. So sorry?
So where does C come in here? The speed of
Okay,
light?
so the J, right, is causal vector field. It's not necessarily null. It's causal. So you have the C is in the wave function. The speed of propagation of the waves is equal to C. But the particles do not necessarily go at speed C. They go at a speed less than or equal to C.
Even the photons.
Even the photons. Right. Even the photons. Although, when they get far away from each other, they become sort of what you expect, right? In the scattering situation, the photon would approach a plane wave, and that one would then go to the speeds.
So the speed of a photon locally could be even bigger than c?
Not bigger, no.
Must
It will
be-
always
must
be
be
less.
less?
Less than we quote, right. So, okay. So, all right, so then, therefore, we're going to get trajectories. So that's, and here's an example of a pair of trajectories. So you start with some initial position. The red one is the photon. The blue one is the electron. You start at some particular position. So this we have solved for a particular initial data. We have solved. We have the wave function. Now we can choose where we want to actually start off the particles and see where they go.
So the wave function is one like you showed us before, which
Yes,
starts
that's the
log
same one.
at 0, 1.
That's the same one, right? So, but now I'm allowed to start at some other place here, right? That's where they were concentrated.
But you're really, it looks like you're really starting at the center of the log.
Yeah, it's a little bit off. You cannot see this, right? So there's a, I will just do more of that. So this is just an example. And you can see that the dotted line corresponds to the non-interacting case, where the trajectories just go right through each other. They don't see each other. Once you turn the interaction on, that's your Compton scattering. They are getting close to each other and then they bounce off. Like that. So that's just for one particular set of initial conditions. But now I have to use typical initial data here, distributed by the initial wave function, and then see how typical this situation is. Right? Yes.
So maybe this is very naive, but once you have these wave functions, can you second quantize, so to speak, and get a relativistic quantum field theory in which these particles are the quanta of the relativistic quantum field?
Normally you go into a pseudo-classical field on space-time and then you second quantize. You do not take a many-body wave function and second quantize, right? So this is really many-body quantum
But
mechanics.
one electron, one photon is not that many bodies.
Well, if we can do two, we can do many.
I mean, I guess the point is that the quantum fields are defined on the space-time, but this is defined on the configuration space-time of two particles. So you have a lot more variables in there. So we don't know how to exactly.
I see what you're saying, I see what you're saying,
Just
I see what you're saying.
Okay, so I'm going to end by showing you another movie here. So this is, so now you're going to look at many different initial conditions for the pairs of particles, right? The locations are dictated by the initial distribution of the wave function, right? So, and with starting, so you see they are concentrated at 0, and the electron is concentrated around 1, but not exactly there, right? So you have a range of possibilities, and you look at all the different dynamics that you can see, and you basically see 4 types of behavior. The two particles going the same direction, this way or that way, or going away from each other, and or coming close and bouncing off.
Why should the two particles be the same color?
Oh, because the color changes according to initial condition. I mean, that's a good point. Usually you would use different colors for that. But here I had the problem that I want to show you this other picture. So the only thing that I want you to note here is that there are trajectories in which photon and electron come together and stay together for a while, and then part ways. So we want to explore that a little bit more, and I'm going to end there. So before I go to that, this is the 10 different, now you can see why I chose. So similar color means the pair that go together. So this green goes with that green and so on, right? And if you do very many of them, what you begin to see is the 4 bumps that you were seeing before in the density plot, right? So this is, if you want, this is a confirmation of equivariance, that the distribution at time t is governed by the solution of the wave equation at time t. So, so let me finish by showing you something that was a little bit of a surprise. that what happens if you start with initial positions that get closer and closer to each other. Let's take the same wave function, right, and just bring the initial positions closer to each other, right? And what we see is that they tend to spend more and more time together before parting ways. And eventually, when they are close enough, it looks like they get a solution which looks like the photon is absorbed into the electron. And at least for this time scale that I've done, they seem to be going happily together. So now you don't see the photon anymore, right? So
But now it is moving at a speed which is less than the velocity of light.
yeah, the speed is just a tiny bit. It's very small difference. Yeah.
Of course, also the mass is chosen here particularly user-friendly, that's
Yeah.
not electron mass leaving or something.
So this clearly calls for much more experimentation with this model, and I have a research experience for undergraduates who is going to help us, explore various regions in the parameter space of this model. We can change the mass, we can change the widths of the Gaussians in the initial data. There are various things that, locations and so on, and then fully understand what are all the possibilities.
What's the deal with the little Red Riding Hood?
Clap, but,
What's the deal with the little Red Riding Hood?
So when I explained to Roddy Tomolka this theory that we had, he came up with this analogy. He said that the fable of the little Red Riding Hood going with her basket in the forest and had cookies in the basket. He said maybe the electron is like the little Red Riding Hood, and he or she has a basket of photons. And once in a while, one of these photons gets shot off. So that was
So yes, but did you ever explain how psi determines x?
no, I will explain that to you. Yeah, I didn't explain it.
I have to go down, that's next time you read it. Shall we? 5 o'clock or something?
Yeah.
4:30?
So, Shadi, suppose I'm a physicist who is hostile to Bohmian mechanics,
Right.
and in particular
Which is
says
that
a
possible?
photon moving below the speed of light is ridiculous. Can you still sell me on this theory just based on the wave function part? Is that still going to be of interest if you leave out the Bohmian part?
Well, my answer to that would be, okay, so first of all, I'm not saying that, so the photons that we are observing are presumably 3 photons, right? So what you see here, if you look at this picture, you see that not only is really way below the speed of light at some point, while it is heavily interacting with the electron, right? The speed becomes almost 0. Right? Because the slope here is the speed. So they are really slowing down while they're interacting.
The
But
Bohmian
once
part.
they move away, right? They presumably they will part ways, and then the photons that we see are actually going with the speed of light. So that would be my answer.
A normal physicist might have thought if in anything remotely like that situation here, that the photon has been absorbed anyway, so
Right. Yeah, they would say that there isn't
Not
even
even-
one, right? I'm saying, well, there is one, but you don't see it because it's stuck to the electron, so that's it's just because the question of the
But doesn't light and matter move at different velocity than light and vacuum?
Sure, but this is
Yeah.
vacuum here.
This is vacuum, yeah.
Yeah, but
It's vacuum, but there is the electron.
There's the electron, right? Oh, but
the electron.
photon is not moving inside the electron.
No, but it's influenced by matter.
Right, it is influenced by
I
matter.
You're right.
Yeah, that's a good
It's
thing.
maybe a good point.
Nice talk, I'm sorry.
I don't know what this topic.
Just push the same button.
thing, but okay. So, I realized halfway through that I may
Yes.
have ended up in this picture. I hope not.
So there's a common
I don't
theme here with
Good.
Kiesling particles and